So, hello, my name is John Pavan, and today I'd like to talk to you about API design principles. So I am currently a team lead at Bloomberg, and this talk was originally developed as a collaboration among engineers at Bloomberg. One of the things that Bloomberg lets us do is set up a community of people that are interested in particular technologies. There's a significant group of people that have gathered around C++ and are dedicated to making it better and making it easier to use both externally and internally to Bloomberg. And I happen to help out with the a particular subsection of that that's dedicated to making APIs better. One of the things that we do is we have a standing offer to review APIs, as well as trying to educate people about how to make their APIs better. So anyways, this talk was developed as a collaboration with that group. So I'm going to begin by talking about the characteristics of good APIs versus bad APIs. I'll then talk about two design philosophies, top-down design versus bottom-up design. I'll talk about how the size of your API's audience, who's using your library or otherwise accessing your code, may impact how much you want to care about the quality of your API design. I'll go through a selection of miscellaneous design considerations. I'll then discuss how application binary interface and application programmer interface impact how you would be able to evolve your API as time goes on. And then I will go through the guiding principles that API review group use in order to try to evaluate APIs. And hopefully you can find that useful in improving your own API design. If there's one thing that I want people to get out of this talk, it's that when you try to develop an API, you should start by considering how someone will actually use it, as opposed to trying to figure out how to expose the cool new algorithm that you have figured out. Okay, so good APIs versus bad APIs. Most of us have used good APIs, and when we use good APIs, we generally don't really notice that they're good APIs because everything just works. It's not something you really have to think that hard about. So we end up with a set of characteristics that a good API generally doesn't need to change in ways that end up breaking clients. That is the people that are using the API. They very often solve business problems kind of quickly and efficiently, and therefore make things easier to deliver. They can be used in a variety of situations, sometimes by design, sometimes it's just kind of a flexible API and people are able to use them to solve problems that the original designer didn't realize. They're relevant for a very long time, years or decades. They're easy to understand and use, particularly by people that are familiar with the domain that they're written for. And they add stability and scalability, and sometimes they even help out with performance. In contrast, I think everyone really notices when they have to use a bad API. The big reason why is that it's a pain and you have to keep doing it. If you only had to do it once, you might not notice, but also it probably wouldn't be that bad of an API. So a lot of times the problems come from platform dependence. When something has to be ported between computers, you may have to completely refactor something. You could have tight coupling between underlying libraries or with hardware dependencies or something like that. But you end up constantly having to redo things. Another characteristic of bad APIs is that they're difficult to use. That it could be that you have to write large amounts of boilerplate code, or the language that they're written in doesn't match what other people who are familiar with the domain might actually be using. And therefore, you constantly have to look things up. Because they don't, the people recognize that they're not especially great APIs, people will then try to fix them. But if they're released out into the wider world, this means that there are going to be lots of deprecations because they can really only deprecate the existing API and try to introduce a new one, which also means that you're going to have to constantly update the API that or code that uses a bad API. It's easy to use them incorrectly. This is a pain if you are either someone that's trying to support the library or someone that's trying to use the library, because you can end up with accidental bugs, or if you're the application developer or the library developer, you might end up having to support use cases that you really weren't intending to support, because otherwise the people using your library really complain. Bad API is also typically very hard to test. This leads to stability issues. Even if you're able to get something right correctly, initially, if you don't have any sort of testing there, or the tests are difficult, or maybe only test the happy path, you can end up with interesting regressions. So another problem with bad APIs. And when someone goes to change a bad API, they may end up producing ABI breakage, which may be a subtle problem and therefore may make it into production, or it might be a noisy problem, but characteristics of bad APIs. So now that we've discussed good APIs versus bad APIs, now I'd like to discuss two design philosophies. It's going to be the first time where I talk about really wanting to focus on how someone is going to use an API. So in my experience, good APIs typically come from top-down design. This means that someone starts by thinking about how someone will actually interact with the library. This could be that someone sits down and writes out some documentation about what the library is actually supposed to do. It may be that they sit down and they write some example code of what they intend for the library to actually do. And that stuff should be saved because you will end up using it later when you create your documentation. But it's a good place to start when developing the interface for your library. So once you have that done, then you can define the API, and only after you have the API should you try to work on the actual implementation. The other way that you could go about building a library is you could have some third-party library that doesn't quite work for your application, and therefore you need to wrap it in a slightly different way. Maybe you need to add the resource allocation is initialization wrapper or something like that. Or it could be that you have a really cool algorithm that you really want to show the rest of the world, and you want to package up in a library. So you start with this implementation, or start with something that you're trying to wrap, and you work backwards from that implementation towards an API. When people do this, it very often leads to unclear boundaries between the underlying implementation and the API itself. This creates a bunch of problems, not the least of which is that leakage of implementation detail into the API itself means that someone that's using that library isn't focused just on their domain knowledge. They also have to worry about what the underlying implementation is. This also leads to problems with testing. So for example, you might have to implement part of the implementation in order to actually mock something out. And very often this means that someone will come along and write an additional layer of abstraction in order to actually be able to use the library that you just wrote in order to try to create additional abstraction. Very often we see this sort of problems if someone tries to wrap up a third-party library. Now I'd like to talk about how the size of your API's audience affects how much you really need to care about API design, or rather, when you should concern yourself with it a little bit more. So when you start developing something, you're probably working with just your team. Your team may just be you. This is the smallest audience that you're going to get. At this point, you can probably make changes to the API or anything else, basically just by recompiling, because you know of every possible use case for your library. But let's say that you have written a great library, you've advertised that other people say, oh, this is awesome, I really want to use this in my code. And at that point, you start having other users inside of your same company. At this point, it becomes much more difficult for you to make changes. The exact details of how much pain it is to make changes kind of depends on the infrastructure, the size of the company, things like that. But you have to deal with anything that is an ABI break, will require getting everyone to relink all of their dependencies. so that you don't have subtly bad behavior. And if you break the APIs, then you're going to have to do bulk promotions. You may have to find every use case for your library and push out PRs to all of the relevant teams. But it is probably still the case that if you have good infrastructure, it may still be possible to make meaningful changes to the API for your library, as long as it's relatively well tracked inside of your company. Let's say that it is even more successful than that, and you decide that it's going to be released to the world. This could be that it becomes an open source project. This could be that your API ends up being the public face for your company going out into the world. At this point, it becomes extremely difficult to make changes. Basically, the only thing that you're able to do is deprecate the existing functions or class and then introduce a new one. And of course, this creates problems for the people that are trying to use your library, because they will then need to move from the deprecated function into your new way of doing things. And even if you do this in a relatively straightforward way, you can end up with situations that persist for years. For example, the dual ABI mode that was introduced with GCC 5.1 created an ABI break for standard string and standard list. There is a handy flag that allows you to compile with the old ABI. And as far as I know, people are still using this, although it's possible that maybe everyone has gotten off of it, but last time I checked, they had not. Microsoft Visual Studio has ABI breaking changes between release and debug builds for most of the standard containers, or a good portion of the standard containers. And therefore, you need to be very careful about mixing the release and debug statuses when you're working on Windows development. So now I'd like to talk about some API design considerations. You should think of your API as a binding, non-breakable contract. The contracts didn't make it into C++20. I guess we probably should be talking about 23. But you should be thinking of your APIs as contracts with the people that are using your library. This is the second time I'm going to talk about really needing to focus on the library's user. So you should think about how the API is going to be used. Again, this is probably the best place to start the thought process of developing the API. You should also think about how can the API be misused. And Andre's talk in this room 2 talks ago is much more detailed about how you can try and prevent that. And if you were not able to see that talk, I would encourage you to at least look at his slides or to watch it once it's available. I guess, on YouTube. So you should focus on how to protect it against misuse. And if it's possible to fail early and loudly, you should try and fail early and loudly. It is much better to have a noisy failure than it is to have a subtle failure, because then people may run for a very long time, or even commit things to disk or ship things off to customers based on bad idea or based on misbehaving code. You should also try to focus on the minimum that you can ship. You should be able to extend the API later, but if you start by having kind of the minimal API, minimum surface that you need to support, it both makes it faster delivery initially, and then you can build utility classes or extend the API itself in order to add functionality later. And you should consider prior art in the same space. So there's probably already libraries for doing things in similar domains. And you should start by you should also look at those libraries and consider not only how people are using things, but are there any bugs, are there any issues that show up with kind of the commonly used libraries that you can solve with a new API, or can be solved by an API that your library provides that are not solved by the existing libraries. When you do go to publish your library, you will need to give some people a reason to switch. So it's useful to think about that early in the process. You should try and follow Meyer's open-close principle. Software entities should be closed, or should be open for extension and closed for modification. In this in kind of the original statement, the idea was that implementation inheritance should be used to extend base classes but not modify them. More recently, there's a much more modern polymorphic version of this, which is that you should use an abstract base class so that the API can be reused, but the implementation can be changed. This ends up being very helpful, not just for hiding implementation differences between platforms or other things, or different versions of your library, but also makes it a lot easier for people that are writing tests because they can makes it easier to mock things out, or makes it easier for you to provide mocks. You should define the preconditions and the postconditions. The preconditions are things that are requirements for arguments, such as, does a file have the correct extension? It can be things that are requirements for state. Does the file have more than 0 bytes? And you should have postconditions. So these are just things that should be true after something has been run. This can be something like there should be the object should be in a particular state, or it can be things about the return values. Like if A is the square root of B, you really should be able to get B back by squaring A, at least within the limits of floating point math. You should define your error handling. Not going to express any preference for how you should do the error handling, but you should pick one method and stick with it. You probably should not mix return values with exceptions. But even if you are picking one of those methods, there are sometimes better and worse ways to do it. So for example, if you had a function that returned a Boolean for success or failure, and on failure, you're supposed to check an error code and an error string that were being populated. This isn't the best way to do it. Basically, if you need to change something like adding an error source, then you end up having an API breakage. It is somewhat better to take the error code and the error string and maybe the error source or other error information and put that into a structure that you might call error info. And then you can have the function just return an error info. Although in this case, you end up with an ODR violation because the library is constructing the error info and expecting the application code to destroy it. You can avoid the ODR violation, but you still get stuck with the API break if you populate the error info when you return false. So no particular guidance, but you should just pick one way and consistently do it that way. You should also consider the library dependencies that your code has. You can end up in a bunch of problematic situations. If you have an application and it uses library A and library B, the library A and library B depend on different versions of library C. It can be very, very difficult to link that application. And if you're, say, library B, and the person's already using library A, they may decide not to use your library because it's more difficult for them to link. For a variety of reasons, avoid cyclic dependencies. And you should try to use libraries that are already likely to be used by people that are interested in the domain that your library is trying to solve problems for. And you should try not to force people to convert types when using your library. So kind of easy kind of roughly compatible types that aren't actually the same would be character versus standard byte, or a regular map versus an unordered map. Not only does this kind of make your code a little bit more difficult to use and therefore less likely to be used, it also has performance implications because you typically induce a copy as people move between their already existing code and your library. You want to try and keep your API as simple as you can. Remember that you're able to extend your API later, either by directly modifying that API or by adding utility classes or helper functions, things like that. But if you publish with a little bit too much complexity that you don't necessarily want to support, trying to remove that later is going to be basically impossible because someone is going to use that complexity for something. You should try and keep portability in mind. This can be the endianness of the endianness of the underlying platform shouldn't be something that gets exposed through your API. Localization shouldn't be exposed through your API. Your API also shouldn't have if-defs by platform. These are all things that you should be able to hide in an abstraction underneath your API, so that someone who is using your library doesn't have to deal with all of these things or abstract all of these things away on top of your library. Okay, so now I'd like to talk about how ABI and API compatibility may impact how you can evolve your code going forward, or evolve your APIs going forward. These are things that probably everyone here is even better at than, or probably better at than I am, so please take this with a grain of salt. Library is basically your library's API, and your compiler's ABI is going to end up being your library's ABI. If you have problems with ABI compatibility, you typically end up with a subtle break. These are things that, the subtle break, in my opinion, is the worst case, because then you end up with things that can make it out in production. Or you get outright crashes. You at least notice that the crash means that something's wrong, and so you can fix it. Then you have to worry about ABI compatibility anytime the library is dynamically linked. And if you're in a situation where you know that everyone always compiles from scratch every time they use your library, this is typically when you are in the small and medium sizes. It may be possible that you can ignore ABI compatibility just because everyone always compiles, everyone always recompiles. But certainly for the largest audiences, that's not an option. However, in all cases, you're going to have to worry at least a little bit about API compatibility. If you have a problem with API compatibility, this basically means that you're not going to be able to build. And you need to care about it anytime you go to publish a library, whether it's a binary publication or a source publication or some other sort of source of publication. And you do have to care about it even when you compile from scratch. So I'm going to attempt to get through this as quickly as possible. This is the list of ABI compatible changes. There will then be a list of ABI incompatible changes, and we'll do the same thing for APIs. So if you are modifying something and you don't want to break the ABI, you are allowed to add new free functions, add and remove friend declarations from the class, add enumerators at the end of the class, but only if the compiler will not need a larger type to represent the enum. You can add static members and functions to classes. You can add non-virtual methods to a class, but not overloads. You can add constructors. You can change default arguments to a different value. Although if you do that, you should be aware that the previously compiled version is going to be using the old default value. You need to remove any you can remove non-virtual private methods. You can add type defs and new types. You can change inline functions to non-inline. But again, you need to be aware that anything that's using the old version will continue to use the old version because it's just going to use, because it has it. For ABI incompatible changes, things that you're not allowed to do, you cannot change a lot of things about methods. The constness, whether or not the const expressions, the return types, the argument positions, the CV qualifiers for arguments and methods, changing template parameters, changing the final and override keywords, changing no except, changing the contents of any inline or templated functions. Can't change the class hierarchy. You cannot add or remove or reorder members of the class or change their types. You cannot add and remove overloads. You cannot inline a member function because the old version of the code will be looking for it in the shared object. You cannot change the access rights to a member function. You cannot add new virtual functions or reorder the virtual functions, or go from non-virtual to virtual or virtual to non-virtual. And you can't override virtual functions. All those things affect the vtable. It's not going to work out well. You cannot change thrown exceptions. This includes the hierarchy of the thrown exceptions. And you can't change the type and CV qualifiers of any global data. There's a lot of things you can't do. API compatible changes are a bit more forgiving. So you can add parameters with default arguments. You can add methods to a class. You can add members to a class. You can add classes. And you can change the order of members and methods. If you are doing something like adding parameters with default arguments, you need to be careful about what things can cast into. Default argument on a pointer, and you decide to add a Boolean just before it, can end up doing funny things, just as an example. API incompatible changes. You cannot remove arguments. You cannot remove public or protected methods, members, or classes. You can't change types for arguments or other member variables. You can't change the name of public and protected members and methods. And you can't move classes between headers. Okay. So now we'll get to the guiding principles. I believe we have 11 of these. And these are things that are hopefully useful to you. They are also a little bit contradictory. And so applying them ends up being a bit of an art. And you do have to consider how much you care about one of them or another one, both in general and for your particular application. So the first of them is that you want to try to make your API as easy to use as possible. This has a bunch of benefits. It shortens the onboarding time, makes it faster for people to figure out how to use your library. It also results in fewer bugs or fewer people doing things that you don't intend for them to do with your API. That both makes the library's user life easier, and it also makes your life easier because you don't have to support as many unexpected uses. It means that people are more likely to use your library, which is probably something that everyone wants. And you should try to follow the principle of least surprise. So the principle of least surprise in this case is someone who has domain knowledge can look at your API, make a guess, and you want them to be right. That doesn't mean that they shouldn't have to read documentation at some point, but most of the time they should be able to guess and get things right. So ways that you can try and make things easy to use is that you should try and pick good names for everything. They should try and be both descriptive and concise. This is a good example of a place where these principles are a little bit contradictory. My personal opinion is that when you are writing an API for general usage, you probably want to give descriptive and concise about equal weight. But if you're writing something for testing, you want to err much more on the descriptive side. So just my personal opinion on that. You want the names to reflect semantic meaning, and you want them to use generally approved parlance. So by semantic meaning, it means that you should talk about what they're actually used for, what they're actually doing, not what they are. That makes it much more likely that the names will continue to be useful in the future because maybe the underlying implementation has to change, but what they're used for ends up being the same. And by generally approved parlance, someone who is knowledgeable in the domain that your library is for should be able to look at it and say, oh yeah, I know what that is, rather than having to try to figure out why you have a client platform adapter and what that means as opposed to an application programmer interface. Just in case anyone's had to work for someone that doesn't like accountants. So you should try and be consistent with your naming, both between the components that you're providing and within components. You want to try and use an appropriate level of abstraction. My favorite example of this, which I will mention at least one more time in this talk, is that if you have a library that's written for a web server, it should be talking about connections and HTTP headers, not sockets. If you're talking about sockets and your web server, you have probably done something a little bit wrong. Another example is that you might want to pass by iterators or ranges as opposed to the container itself when you need to access the contents of a container. This is something that, for example, the standard algorithm library does. You also want to try and make your code as hard to misuse as possible. Check Andre's talk. You want to have unambiguous and sufficiently narrow contracts. Write the documentation for your APIs a little bit like a lawyer. You want to try to follow any generally accepted coding conventions. This is kind of following along with the idea of the principle of least surprise. You want people who are already familiar with the domain to be able to make a good guess about what something is supposed to do and have it be right. And you want to have the API behave exactly how your users will expect it to behave. My personal opinion, a good example of hard to misuse is Chronos time point, in particular how it deals with time zones. So you can get the UTC time pretty easily by just doing system clock now. And if you need to convert to the local time, you can use a utility class from date in order to just make it zoned. And date also provides something to get the current time zone from the computer. So it just happens to be an example I like. You want to make sure that your API is well documented. Functionally, if something is not documented, it doesn't exist for people that are trying to use a library, at least for the first time. This is the place where when you start off with the user-oriented design, you can take all of that initial work and use it to start your documentation. So you want to document everything that is publicly available. You want to have clear, concise, explicit, and unambiguous contract definitions. Again, think a little bit like a lawyer. You want to try and provide tutorials. This would be a place where you could reuse some of that example code that you were working on, or that you may have used when you were started out with that user-oriented design. And you should have some sort of documentation style. Does not matter to me what that style is, but you should have a style. There's a bunch of them around. Just pick one that you like probably, and then try and stick with it. You want to try to make your API minimally complete. This means that you want to try to include everything that is necessary, but exclude everything that can be efficiently created in terms of the stuff that was necessary. This makes it easier for you to maintain abstraction, that people can't distinguish between the implementations, and to maintain the representational invariance, so basically the tautologies of a particular API. A good example of this design, or of this sort of thing, is if you consider how mutex and lockguard interact. Mutex is relatively minimal in that it provides functions for locking and unlocking. And then lockguard is kind of a utility class that works with it in order to provide the resource allocation as initialization pattern so that you can use it in an exception-safe way. You want to try to make everything loosely coupled. This is both between the API layer and any sort of underlying implementation, and also between your components and among your components. So if you have two things in different components that are strongly coupled, they should probably be part of the same components, or part of the same component. But if you have something that is in the same component that is loosely coupled, they should probably be parts of different components. Suggestions here, again, avoid cyclic dependencies, is generally good advice. And you should try to only include and import what your particular component directly relies on. You can use things like callbacks or the observer pattern or in order to break dependencies. This can be particularly helpful when you're trying to make things so that they're easily testable. And you can also use the mediator pattern, something along the lines of a manager component, to have a single point of access for multiple resources. This can also make it much easier for people that are trying to use your library if the resources that are available may depend on something like a configuration. You also should try to avoid leaking implementation details. This is basically Hiram's law. Every observable property of an interface will eventually be depended upon by somebody. So you should strive to make the set of observable properties as close to the contract promised by your API. Basically, try to work everything in terms of domain stuff. If your implementation is leaking through into your API, then that makes it so that the people that are using your library can't rely on their domain knowledge and instead have to learn the details of your implementation. This makes it much more difficult for them to use it. It makes them less likely to use it as well. It also means that if anyone is actually using your library and you need to make changes to the underlying implementation, then, or to the API, then you really end up quite stuck because you've already exposed that bits of implementation to the end users and someone's using them for something. It's also easier for clients to upgrade because they can just switch over to the next version of your library as opposed to having to modify their code before doing so. It also makes things easier to test because your library can be self-contained, and therefore you have a lot more control. And if you do have to mock something out in order to test, then you don't have to partially implement that in your mocks. I think I already said most of this. Oh yeah, I should avoid exposing any sort of internal types. I think that was implied but not explicitly stated. And if you rely on any other libraries or anything else, you want to avoid exposing those types and functions directly. It is unfortunately pretty easy to leak implementation details in ways that seem benign, especially when you're working with a small group or even a medium-sized group, because of course, why would someone do something slightly crazy? Here we just have an example where we have a class that contains a value. We have a function that increments the value and returns a reference to the value. And when we increment the value, we check to see if it's crossed some threshold, and then we return a value. Now the problem here is that even though this is kind of a nice performance boost, someone can grab this guy and then modify it directly. And if you have a sufficiently wide audience, you're going to get at least a couple bug reports saying, hey, when I modify this value directly, it doesn't check the threshold anymore. And whether or not you decide you want to support that use case, you at least had to read those emails and it probably raised your blood pressure. So save yourself some pain and don't make this particular mistake. I think last time I made that mistake was 20 years ago. You also need to design things in terms of longevity. So the people who are using your library may have different needs in 5 years, 10 years than they do now. And as a consequence, your API may need to change. It can also be that the hardware that they're running on is different. And therefore, the requirements, platform requirements can change. So this is another reason you shouldn't make anything that is directly tied to a particular platform or that you know won't work on a particular platform. Say your library is working right now on a supercomputer, and it may be in 10 years it will work on a cell phone. Computers get better surprisingly quickly. You should remember that your API doesn't have to be released with the full feature set. You can add them incrementally as they're needed. Just kind of an example of some way that you may be able to make things a little bit better, although this does still induce an ABI breakage when things get added, is if you had a function that does something in response to a request, it may be that you populate a name and a value based on the request. And let's say at some point you need to add some additional thing like a code return or something like that. If you do it this way, you're going to have an API breakage. But if you take the name and the value and put them inside of a response, then you can populate the response. And if you need to add things to that response, people still have to relink, but they at least don't have to modify the code by hand if they don't care about that additional field. You also want to try to avoid boilerplate code whenever possible. In my mind, a good measure of how well suited a particular API is or a particular library is to a particular task is basically how little code you need to do in order to accomplish that task. If you go back far enough, you can kind of look at how much code is necessary to make a simple text editor and something like less-teef or motif versus how easy they were to make in GTK or Qt. It goes from several hundred lines of code down to like 30. These days, you can probably do it in 5. Things have gotten better, but you should try to add things or try to write things in such a way that they don't require large amounts of boilerplate code. It'll make your life easier. It'll make your users happier. And one of the easy ways to do this is to work at the right level of abstraction. So again, if you have an API for a web server, you should be talking about HTTP requests and headers. You shouldn't be talking about sockets. It's just sockets are just the wrong layer of abstraction that should be hidden further down in the library. So it shouldn't be something that's developed that someone who is developing a web server should have to worry about. An easy way to reduce the amount of boilerplate code is to provide utility functions and to provide helpers which just handle that repetitive code. This not only makes the library's user happier because they have to do less typing, it also makes your life a lot easier because when you are doing testing, you have a lot of the common use cases already well defined. One of the things that we can take from the language about how things have gotten better over time, particularly around boilerplate code, is if you go back far enough and you wanted to have a custom sort, you would kind of have to build this function object where your bound variable gets put in as a member variable, it gets passed into the constructor, and then you have to define some sort of operator that would take A and B. You can save 4 or 5 lines of code by using a lambda nowadays. Does exactly the same thing, has exactly the same performance characteristics, is somewhat easier to read as well because for this custom sort method, it's likely to be far away from where the sort is actually used, where the lambda method is going to be contextually in line. You want to make sure that everything is platform independent, at least at the API level. Your underlying implementation does not have to be platform independent. So you don't want an API to have something that only works on one system. Similarly, you also don't want to do anything that you know for sure will not work on one system. Easy places where where you can run into this is kind of looking at what would work on Windows versus what would work on POSIX. Anything that depends on endianness shouldn't be part of the API. And you may end up having to deal with, or at least be aware of, various vendor compiler issues as you kind of develop your APIs. Although you can decide maybe you're not going to support AIX given the choice. You also should try to follow the golden rule of API design, which is that you should write tests for the code that uses your API. We call this designing for test drivers. So your API should basically provide test drivers for people that are using your code. There should be some way for people to mock out the functionality that your class has so they can say exercise all of the error conditions in an easy way rather than trying to force your code into a method that, into some sort of method that, into a state that actually induces those error codes. Say, for example, if you are abstracting, or if your library is providing some sort of TCP connection, if you actually have a TCP connection, it's very hard to induce interesting error methods for that TCP and TCP connections, at least at will. And so being able to provide those mock implementations becomes very, very handy. I apologize, I thought my phone was off. You can also try and make things a bit easier by trying to follow the interface segregation principle. That is that you should try and have smaller interfaces with distinct behaviors as opposed to having fewer large interfaces. The fewer large interfaces are something that kind of happen naturally over time. So be aware of that as your library evolves. And you want to also try and provide mechanisms to break dependencies in order to let drivers run in isolation. You also need to write your API in such a way that you are able to test your underlying implementation. It's not exactly the same thing, but it's related. So you basically need to provide mechanisms for yourself that allow you to stub out any underlying system or library calls so that you can test that your library is having the correct behavior under error conditions or just in order to kind of save the pain of the setup. A suggestion for how you might want to do this is to use the pointer implementation idiom. So we just kind of have a primary class, and then you have a primary implementation, which is private inside the primary class. You may have a function that is called calculate, it does something with some data. But the exact method of calculation is dependent on something. It could be the hardware that it's running on, whether or not there's a GPU. Maybe if the data is larger than a certain size, a different algorithm is better. But there may be more than one way to do these calculations. Rather than trying to set up your tests so that you force calculate to go down a particular route, your primary implementation can just provide the different options directly as public methods, and therefore they're just a lot easier to call in your testing code. So those are the principles of API design as we attempt to use them, at least in our little API review group. I hope that I've convinced you that it's important to write good APIs, and that you should begin by trying to consider how they're going to be used. Consider your user first. And I hope that you find the principles of API design as reviewed in this talk useful to you as you try to build your own APIs and support your libraries. Thank you for taking the time to listen to my talk. If you're interested in how C++ is used at Bloomberg, we have a link and a QR code. We are hiring if anyone is interested. And if you want to reach out to me directly, this is my email.